Swayam Prabha. Digital India. Educated India.
Alright, welcome everyone. Let's get started. So, we started looking at some basics of lattices last time. As I already said, what we are looking at in this course is really just a very superficial treatment of lattices, which is a very rich theory in itself. But nevertheless, we defined lattices, we defined a few important quantities. In particular, we defined the successive minima, right, lambda 1 to lambda n, and we defined some useful and interesting problems on lattices, the shortest vector, closest vector, shortest independent vectors problem and so on, and approximate versions of those as well. Now, as I told you last time, these are the classic problems on lattices that have been studied for a very long time. Surprisingly, though, there is still progress that's being made on solving these problems, but only in the improvements that we get are very modest. So, they remain exponential time algorithms, but we can still get some modest improvements. So, we really believe that these problems are hard, and not only do we believe they are hard for a classical computer, we also believe they are hard for a quantum computer. All of you will remember that I talked about how problems on lattices correspond to problems in non-commutative groups of the dihedral hidden subgroup problem. So, we do not have any nice way that we know of solving these problems even using a quantum computer. Okay, so fine. So, assuming that we are good to go with lattices, which is what is currently believed, let us try to see how to do some cryptography using lattices, right. And last time I also told you that these classic problems which we defined, the shortest vector, closest vector problem being the main two, these are not immediately useful for building cryptography. So, what we will do is we will actually look at sort of other these same lattice problems disguised as other problems, notably this learning with errors problem and the short integer solutions problem, which we also saw last time, and we will see how to build some cryptography using that. Okay. Now, I will again mention that building cryptography from these lattice problems is a very rich and diverse area of research. Notably, there are things that we can do from lattices that we did not even know how to do in the pre-quantum setting. So, it is not just that lattices are giving us post-quantum or quantum resistant versions of things that we could do otherwise, but they are also giving us new and amazing things that we just did not know how to do before. So, I would like to show you at least one or two in the few more lectures that we have remaining, but before that let us get a few more basics out of the way. Okay. So, with all that, let me sort of dive right in. So, what we will do today is we will build encryption, just vanilla public key encryption from the learning with errors problem. Okay. So, we defined the learning with errors problem last time. Can anyone remind the class what is the intuitive one line description of learning with errors? Let me define it for you again. Okay. So, learning with errors. Okay. So, this is sort of abbreviated as LWE, no prizes for guessing why. Okay. And we have two versions of this. There is a search and a decision version. Let me define the search version first. So, we will denote this as SLWE with parameters N, M, Q and Chi. Okay, and this is the question of finding S, a vector S, which lives in ZQ to the N, given AI AIS plus EI such that S was chosen randomly from ZQ to the N, so were AI in fact, okay, and EI is chosen from some distribution chi, and I am giving you M of these samples, okay. So, find S given these noisy inner products. So, I have inner products with respect to a secret vector S, and I am giving you these inner products perturbed with a little bit of noise, and the goal is going to be to find this secret vector. So, the one line intuitive description I was referring to was this, that think of noisy inner products and you are trying to find the secret vector with respect to which these inner products are generated. Okay, so this is the search version. There is also a decision version. Okay, and when I just write LWE NMQ chi, I will be referring to the decision version, and this is simply distinguish the above samples from uniform. Alright. So, obviously the decision version is it seems like a stronger assumption, because even if I can solve the search version, then I can certainly solve the decision version. Right? If I can search and recover the secret vector S, then certainly I know that this is not the uniform distribution. But if I can solve the decision version, it is not immediately obvious how I can solve the search version. Nevertheless, the other direction also holds true. Okay, so given an efficient algorithm for solving the decision version, I can also use that to solve the search version, but we will not do this reduction in class. Now, one important quantity here that I did not define is this this distribution chi. So, everything else here is defined, right. So, n is the dimension of the vector, m is the number of samples I am giving you, right, and chi is a distribution from which I take the error. So, how should I choose this error? Obviously it has to be something small. Now, can you tell me why it should be small? For instance, why can I not choose EI from ZQ? What happens? That is exactly right. The inner product will no longer, the output will no longer be a noisy inner product, it will just be statistically random, right, because I am giving you random plus something over a finite field. So, it's just going to be statistically uniform. So, the problem will not make any sense in that case. Okay. So, this is the search and the decision version of the problem. Now, this chi I was talking about, this chi I am not, for the moment I am not going to define it. So, even last time I said that you can think of it for simplicity to just be 0 and 1, like sampling the error from, let us say, -1 1 or 0 1. This distribution actually matters, like when you do these reductions between learning with errors and these classic lattice problems like SVP and so on, shortest vector problem and so on. At that time, the distribution of error here really matters in for the reduction to work. And in fact, since I have already said so much about it, it will turn out that the nicest distribution here that works is a so called discrete Gaussian distribution. I am not going to define it in this class, at least that is not my plan, we will see. Yeah, so just think of a Gaussian distribution, but discretized over integer points. Okay. So, this is just for your knowledge, but yeah, we will not really use any properties of it in what what we do in class, except the fact that with overwhelming probability we expect the norm of this to be bounded. We expect the norm to be small. So, everybody knows what Gaussian looks like, right. So, it's something like this, right. So, it's something like this, and now I am sort of discretizing it. So, basically it will be something like this. So, what this means is that if my mean is 0, right, then whatever is this distance, the standard deviation of this Gaussian, I can expect that my sample will not be larger than that, right. So, everybody knows this, all of us have played with this hundreds of times. So, that is really the only property that we will use in class for the purpose of constructing cryptography. But I want you to know that underlying this distribution does matter, because it is how we connect this problem to the the classic problems on lattices that we talked about. So, let me just write down what we know about the hardness of lattices of LWE, again a little informally. So, I will not prove this. So, there is a seminal work by Oded Regev which in fact introduced this problem, and for which he won the very prestigious Gödel Prize. Okay. And then there is a follow up work by Brakersky et al. Which improves the result. So, I am just writing informally. So, it was shown by these works and other works also, I should say, by these and other works, that for appropriate choices of parameters. So, what are our parameters? You know this n, m, q and chi. LWE, n, m, q, chi is, I should say search LWE, is as hard as solving worst case lattice problems such as SIVP or something known as gap SVP, which is a problem related to SVP, but with an additional promise that makes it easier. Okay. So, is solving worst case lattice problems such as gap SVP and SIVP with approximation factor poly n q over gamma, and gamma here is it's actually the standard deviation of the Gaussian that I was talking about, but let us just say something related to chi, because for our purpose it really does not matter. Okay. So, we believe that LWE is hard. Here I should mention that we really are using the approximate version of these underlying problems. Okay. So, if you remember how we defined this shortest vector problem and so on, we had approximate versions where we said that even if you can't get the exact solution, if you can get it up to some approximation, that that is still useful. So, here we are using the approximate version of these problems, and I should mention that for these approximation factors, these problems are not known to be NP hard. Okay, so really just like with the rest of cryptography, we are conjecturing that these problems for these approximation factors are hard. This is just based on our knowledge of what are the best known algorithms to solve them. Okay, so I will just make a note here that the best known algorithms for 2 to the k approximation of this gap SVP and SIVP run in time 2 to the order n over k. Okay. So, you can see that as the approximation factor gets bigger, so as k gets bigger, okay, the time to run this these algorithms will get smaller. So, that is why when I assume the hardness of LWE with such parameters that this underlying approximation factor becomes very large, then I have to worry. So, there is a lot of science even behind how to choose these parameters and so on in the real world. I can always choose it very conservatively, right, so that the problem is very hard. Why don't we do that in practice?
Take more computer resources.
That's right. So, it becomes less efficient. I mean, the real system will become less efficient if I choose if I focus on choosing parameters only based on security guarantees, then efficiency will suffer. Okay, so one more really handy thing about learning with errors is that there's actually there's a lot of flexibility in how you choose the distributions from which the secret and the error is sampled. Okay, so there's a particular form of LWE called the Hermite normal form, which I will quickly define, and that is what we will use. Okay, so we will the Hermite normal form, okay, or we can also call it short secret LWE, is like LWE, but with the difference that the secret S is also chosen from chi, from the error distribution chi. Okay. So, remember we are generating AS plus E, right, and previously we were talking about when we defined it last time as well as today, we were sampling S uniformly from ZQ to the N, right, uniformly. So, these are large entries, and I was telling you how the error obviously has to have small entries, about otherwise there is no sense in defining this problem. So, the Hermite normal form or the short secret LWE says that even if you sample the secret from the same low norm error distribution, whatever you sample the error from, sample the secret from the same distribution, then also LWE remains hard. Okay, so there is quite a cute proof for this, maybe we can do it if time permits. Okay, but first I would like to just show you public key encryption from this. Now, public key encryption from learning with errors, there are many different ways of doing it. I will show the simplest one. Okay, so let's construct public key encryption. Okay, so we have our key gen algorithm first, right. So, remember this takes a security parameter lambda, and sample S from chi to the n, okay, A uniformly from ZQ, let us think of it as a square matrix, and error E also from chi to the n, okay, and let the public key be equal to A and Y, which is S transpose A plus E transpose. Okay, so this is going to be in ZQ n by n cross ZQ n. Okay, so basically my public key is a matrix and my secret key is my public key is a matrix together with an LWE sample generated with respect to that matrix, and my secret key is the LWE error. Okay, so my secret key is going to be S. Okay, so I will write it here so that everyone remembers. So public is A and S transpose A plus E transpose, and the secret key is S. Okay, so now I want to encrypt so this will take the public key and the message M. For now I am just going to think of M as a bit. Okay, so I just want to encrypt a bit. So what will I do? Well, I will compute A as or let me first sample. Okay, so sample R and X from chi to the n and also X prime from chi. Okay, and now compute A as AR plus X and B as Y transpose R plus X prime plus M Q over 2 mod Q. All this is mod Q. It is all over set Q. Okay, and you output A comma B. Alright. So, what did we do? We generated more LWE samples. So, our public key was already an LWE instance, right? The secret key was the LWE secret, no prizes for guessing that. The ciphertext is LWE samples generated with respect to the public key. So, now the public key is itself a matrix and a vector, right? I am going to now use those as the as the sort of the seeds for LWE. So, those will be the I should not say seeds, those as the sort of the public labels or matrices of LWE. Okay, so I will now use those to generate more LWE samples. Okay. Now, can anyone tell me how to decrypt? So, now I am given S and I am given A and B. So, let me compute, I compute S transpose A. So, what is this? This is S transpose AR plus X, right? Yeah. So, this is okay. So, this is S transpose AR plus S transpose X. Now, what is B? B is Y transpose R plus X prime plus M Q over 2. So, let me expand. What was Y? Y was S transpose A plus E transpose, right, times R plus X prime plus M Q over 2. Okay, so, this is S transpose AR plus E transpose R plus X prime plus M Q over 2. Now, the key thing to observe is that the only big terms that occur in S transpose A as well as B are these. Why is that? Remember that we sampled S as well as X from the error distribution. So, once again think of binary for simplicity. Okay. So, S is binary, let us say, X is also binary, okay. E is also binary, R is also binary, X prime is also binary. So, let me highlight the binary things, or the error distribution things with pink. So, now what does this mean? Basically, if I subtract if I subtract S transpose A from B, then this large term which I have, right, this large term, this will get cancelled out, right. If I do B minus S transpose A, the large term gets cancelled out, okay. And what do I get? I get some S transpose X plus E transpose R, right, plus X prime plus M Q over 2. This is what I get. Now, I claim that all of these are quite small. Okay. Now, my message, remember I said it is a bit. So, it is either 0 or 1, and I am scaling it with Q over 2. So, think of this is 0 to Q, let us say. Okay. So, Q over 2 is somewhere here. So, now suppose I can bound this error term, let me say I can bound it by some B, okay, and this B, let us say, is quite small. So, suppose I can say that B is going to be at most Q over 4. Then what happens when my message is 0? Then 0 plus some B will be somewhere here, right, and when my message is 1, then Q over 2 plus B will be here. So, what can I do? I can recover the message bit just by seeing whether this subtraction gave me something which is close to 0 or is it close to Q over 2. This lets me recover the message bit. Is the correctness clear? So, we need to set the parameters. For correctness we need to ensure that the error will be small. Let us do that, but at least at a high level is this idea clear? Okay. So, let us write down correctness. Okay. So, let me say that the support of chi. So, again not getting into the distribution of chi, but if I can say that this is my support for this, for any sample chosen from chi, I can bound its value, okay. So, it lives in this set. You will see why I am choosing it like that. Suppose this, this is doable. By the way, what is the only possible hurdle in setting chi to have this support? You have to make sure that for this kind of a chi, the LWE problem remains hard. Okay, so I hope that you can see that there is a sort of a tension between correctness and security. If I have very large error, then security will be better and better, right, but correctness will be harder and harder, and vice versa. If I have a very small error, correctness will become easier, but hardness will become worse. Okay. So, suppose that my support is like this. Okay, then what was my final error? Let me remember. So, my final error is so this is B minus S transpose A, right. So, this is S transpose X plus E transpose R plus X prime. You can confirm, right, S transpose X plus E transpose R plus X prime. This was my final error, okay. And here this S is of length n, x is of length n, this is also of length n, this is of length n, and this is of length 1. Okay. So, given that S, x, E, R and x prime are all sampled from chi and I have a bound on chi, I should be able to bound this whole quantity, right. And a very simple bound is q over 4 to n plus 1 times 2n plus 1, which is q over 4. This is a very simple bound. You can see how it comes about. Okay, so basically when I take inner product of S and X, every entry will get squared, right. So, I will get q over 4 to n plus 1, and then there are 2n of these, right. There is in this inner product. So, the first one is an inner product of 2 n length vectors, the second is also of 2 n length vectors, right. So, x prime is just a scalar, right. So, it can be bounded by square root of this quantity, which means it can be bounded by the quantity itself. So, basically adding it up I can get this very trivial bound. So, as long as you know the final error remains bounded, I am going to get correctness. And once again, what did we use here? We just used this picture, right. So, I am only encoding bits. So, if my error is bounded and I am scaling my bit by a sufficiently large scaling factor, then what happens is that the error does not cause enough perturbation for a 0 to flip as 1 or 1 to flip as 0, right. When can 1 flip as 0? If it wraps around q and comes back, because we are in ZQ.